Hello and welcome to another episode of Mr. Walker's Chemistry. Today we're just continuing on with bonding. So in the previous video we learned about ionic bonds and how that is between a metal and non-metal, and that the metal is giving up an electron to the non-metal, which is stealing the electron. And in order for an electron to be stolen, we said that the electronegativity between the electrons had to be greater than 1.7. So now that we're on covalent bonding, we have to ask ourselves, what if the electronegativity difference between the two atoms is not greater than 1.7? And that will result in a covalent bond. So think about the periodic table and where you could have a difference of less than 1.7 on the electronegativity trend. And you have to look at it and you find that generally it's the non-metals. So if I can type in here, where is it less than that? It's the non-metals is what we want. All right. And so then rather than steal, they're going to share. All right. So make sure you've got that in your notes. Oops. And so now we can be quote unquote happy. In other words, we can have 8 valence electrons whether we steal or share. So if we look at chlorine and we draw the Lewis dot structure for chlorine, all right, we'll find that it has 7 valence electrons. All right, so we need one more to make chlorine happy. Well, if I've got 2 chlorine atoms, how do you make them both happy? Well, you share 1 electron. Okay, so by sharing 1 electron from each chlorine atom, we can generate a covalent bond. So here's a little bit of practice for you. We'll definitely do a lot more in class. Just go ahead and try these. All right, so draw out iodine, oxygen, and nitrogen, and tell me how many each need to share to be happy. Okay, and then we'll look at some examples of how we can do this between a whole lot of different atoms. Alright, so hopefully you drew those out and you found that iodine has 7 valence electrons, which means it needs to share 1. Oxygen has 6, 2 to share. Nitrogen has 5, with 3 to share. And how do you know how many you have to share? Well, it's all the dots that are by themselves. If you have 2 dots paired up, they don't share. Here are some other examples. Okay. So if we have nitrogen and 3 fluorine atoms, we can put 1 nitrogen in the middle and then bond the 3 fluorines around. And when you count them, you'll see that each have 8 valence electrons. Same thing with the carbon and 4 hydrogens and carbon and 4 fluorines. All right, each of those will work just fine. Some other examples. Okay, if we have a couple of hydrogen atoms and an oxygen atom, we can bond those together to form water. Okay, so to summarize covalent bonds, each shared pair of electrons is a bond. Okay, and now we've created molecules. So if you share 1 pair of electrons, you create a single bond. If you share 2, you create a double, and 3, a triple. We cannot share 4. There's no such thing as a quadruple bond. It just doesn't happen. Okay, so the more pairs, the stronger the bond. All right, and the stronger the bond, the closer the atoms are together. Okay, so remember, they're sharing and they're pulling each other together, closer and closer and closer. So the more bonds you have, the stronger the overall bond, and the closer they are together. All right, so go back to your practice, look at iodine, oxygen, and nitrogen again, and tell me how many bonds they have. All right, moving on here. Some more examples. Carbon dioxide. Okay, 1 carbon atom in the middle, 2 oxygens double bonded to the carbon, and you can have ethene here. Okay, and this has the carbons with the triple bond and then the single bonds outside. and this makes everything happy. Now hydrogen only needs 2 valence electrons to be happy, so that's why it's only got the 1 bond without any extra dots. Okay, but now there is one extra thing with covalent bonds that ionic bonds don't have, and that is polarity. Alright, so when we look at ionic bonds, you just have one completely positive atom and one completely negative atom that just stick together because of magnetism. Well, with covalent we don't have that. We just have shared electrons, so both atoms are still relatively neutral. The problem is that sometimes those electrons hang around one atom more than another. And when that happens, we have an unequal sharing. Alright, so if we look at water, you hopefully studied water in biology at some point and learned that it was polar, which is why it's considered to be the quote-unquote universal solvent, and is what allows all life as we know it to exist. So when we look at it, you've got H2O, so the oxygen is holding on to the electrons slightly longer. The reason for that is oxygen is more polar than the hydrogen. Remember, hydrogen's all the way on the left, oxygen almost all the way to the right. So as we go across the periodic table, then you increase your electronegativity. So oxygen more electronegative than hydrogen, meaning it pulls electrons closer to it most of the time. As a result of that, as a result of holding on to electrons more often, oxygen becomes more negative. Okay, not very much more, but just enough. Okay, and as a result we get a polar bond. Okay, so this also results in something called hydrogen bonding. So I've got so that's what we're talking about with a hydrogen bond. I've got a picture here also to help you see what's going on. Alright, so here we have water. Alright, and water has the electronegative oxygen on one side and the hydrogens down to the other side. So that creates a dipole. Di meaning two, and then a pole meaning opposite ends. Okay, so we've got a negative end up here and a positive end here and here. Whereas with carbon dioxide, because it's linear, alright, they're lined up straight, even though oxygen is partially negative on each side, it results in no net dipole because this negative cancels this negative. And so overall CO2 is considered to be neutral and not to have any partial charge or full charge. So we'll go over that more in class. I'm not sure that in this video it's really easy to see or understand, so we'll be doing more of that in class. So we do need to move on though to naming, more nomenclature. How do we name these molecules? Alright, so we've got kind of the basics. Alright, so if we're combining elements that do not contain a metal, which is going to be most covalent bonds, for example oxygen. Okay, if we put oxygen with nitrogen, okay, we have nitrogen oxide, so we change the ending of the second element to IDE. So how do you know which element comes second? Part of it's practice, and typically it's the one that is more electronegative. Okay, so nitrogen is less electronegative than oxygen, so when you bind nitrogen and oxygen together, then you put the oxygen second. We also have prefixes. Make sure you write these down and memorize them. Alright, you need to know these. Mono for 1, di 2, tri 3, tetra 4, penta 5, and hexa 6. We probably won't go too much more, but 7 is hepta, octa is 8, nona is 9, and deca is 10. But these are the 6 you should really know. So again, mono 1, di 2, tri 3, tetra 4, penta 5, hexa 6, hepta 7, octa 8, nona 9. So hepta, octa, nona, deca. Okay, those are your next ways. Alright, so if there's only one atom of the first element, don't use mono. Okay, you could say, for example, monosulfur dioxide, but that's kind of repetitive, so we just say sulfur dioxide. Generally, you won't see mono very often. Things I can think of are like carbon monoxide, yet generally you'll see it. Diphosphorus pentoxide, okay, so we have 2 phosphorus bonded to 5 oxygens. So diphosphorus pentoxide, and here's a phosphorus trichloride. So the reason we have to use prefixes with covalent is that you don't know how many you have, unlike ionic. Okay, with ionic, it was very much of a very simple. It was just you have this charge and this charge, and you need to cancel it to become neutral, so you can easily figure out how many you need. Whereas with covalent bonding, you can't really do that. It's much more you can have lots of different combinations. Like you could have PO3 instead of P2O5, so you have to use the prefixes, and that's where it all comes from. Okay, now right now in your mind you need to get things straight. Okay, you cannot use prefixes when you're talking about ions. So if you have a metal and a non-metal bonding together, do not use a prefix. So that means that you need to go and take your time and look at the periodic table, look at the elements that you're bonding, and say, okay, do I have a metal, non-metal? Yes or no? If you do, okay, then you're going to go to ionic, and you don't use prefixes, and you figure out charges. If it's a non-metal, okay, then you have a covalent bond, and you need to figure out how many you have and draw your Lewis dots and everything. So covalent becomes much harder than ionic, but it's essential that you take your time to figure them out. Alright, so let me give you a few pieces of practice in here. Alright, so let's see, let's have, if you do NO3, okay, draw the Lewis dot and name it. Alright, so how are you going to bond them all together? And I want you to name it. Do the same thing for water. Oops, okay. Try, let's do P03 and P2O5. Do the Lewis dots and name them. Notice, if you forgot how to name them, just go back one little bit in the video and see it. HF. What else could I think of to do pretty quickly? That should be good. Okay, so go ahead and try and name all of those and draw the Lewis dots and try and connect all the atoms together, and you'll have plenty of practice with this in class because it is hard. This is probably the hardest part of bonding. Alright, so that wraps up covalent bonding. We're going to talk more about polarity in class, but this gives you a pretty good idea of what it's about. Remember, it's all about sharing and not stealing, which is all predicated on electronegativity. Alright, so that's it. Hope you learned something. Be sure to ask questions in class if you need it or on Edmodo.